this lecture we look at some additional points and topics in the various areas covered in this course. Towards the later half of the previous lecture, I had provided a summary of the topics covered in this course on manufacturing systems management. This course spends considerable amount of time on cellular manufacturing and then takes the student through some topics in just in time manufacturing, and then we studied synchronous manufacturing or theory of constraints, and towards the end we also looked at some topics in flexible manufacturing. A summary of what was covered in this course was provided towards the latter half of the previous lecture. Now in this lecture some additional points are given, and these points are added to this course primarily based on some inputs that have been received from the reviewers. So we will add the points on the topics in the order in which these topics have been covered in this course. So the first topic that was covered in this course is cellular manufacturing, and we would look at these additional points with respect to cellular manufacturing. We spent a considerable amount of time in this course understanding algorithms that can be used particularly in designing or creating a cellular manufacturing system, as well as in operational issues such as operator allocation, scheduling and sequencing, and so on. We did provide with some inputs on the extent of use of these techniques. We did provide in an earlier slide that in a survey that was conducted several years ago, it was pointed out that nearly 32 of the 53 companies that were surveyed used some quantitative modeling in the design and operation of cellular manufacturing. Now several years have passed since that research article appeared, and there is increasing application of these techniques that we have seen, particularly techniques centered around operations research that are used extensively to create and design cellular manufacturing systems. But primarily production flow analysis as a technique is used extensively because it is a very simple and efficient method to create manufacturing cells. Second aspect that we would look at is availability of software with respect to cellular manufacturing system design. Now the number of models and algorithms that we have seen, we have looked at several objectives, starting from the overall objective of minimizing the cost, which also translates into in some ways minimizing the inter-cell moves or exceptions. If a part that is attached to one cell moves to another cell, then it creates an inter-cell move. There are times when we even defined inter-cell move as two moves, when a part moves from one cell and comes back to the same cell or the parent cell. So the primary objective in cell formation or cellular manufacturing creation or design is to minimize inter-cell moves. We also said that there could be a need to have extra machines, and there are cost implications because we have to use extra machines. We also said that we could do part subcontracting or operation subcontracting, and all these are used as ways to reduce the inter-cell moves. The mathematical modeling algorithms that we saw look at minimizing inter-cell moves directly or minimizing distance if machines were modeled as points and p-median models are used. There are several algorithms and methods available which also talk about overall cost minimization. They also talk about increasing the utilization and so on. So, there are several objectives. Now, in terms of number of constraints, there are different types of constraints. The number of cells that we would like to have, an upper and lower limit on them. The cell size would act as a constraint. Sometimes budget or money would act as a constraint. There could also be other constraints such as utilization and so on. We saw models which used 0-1 data or incidence data, and we also saw models that used data that covered the processing times or that included the processing times, sequences and so on. So, there are several parameters that go into the design of cellular manufacturing system, and different algorithms used some or all of these as inputs to the algorithms to provide solutions to cell manufacturing design. Now, some effort has gone in to create software, and this software can be used by designers to create cellular manufacturing. And this software, in this software the user can define cell size, define the number of cells, could define the parameters such as processing time or incidence data, and the users can also configure these cells as well as do a performance analysis to understand how these cells behave. So, in some ways all the algorithms that we have seen that are used to model the cell formation, some or part of them can also go into these software, and such software can be used by practitioners to create or design cells. As we have seen in this course, several of these also translate into mathematical models which can be solved using optimization. So, through a combination of optimization, operations research techniques and math programming and so on, as well as user friendly software, it is indeed possible to create cells very efficiently. The third issue that we look at is implementation challenges. It has been mentioned also in the lecture that there is the transition period. Cellular manufacturing essentially talks about creating manufacturing cells, which would also involve moving machines from one place to another and physically bringing machines which are functionally dissimilar, but similar in terms of manufacturing operations of a set of parts together. So, there is a changeover period or a transition period. This would involve several months depending on the scale, the size and the scope of the cellular manufacturing. Now, the organization also has to carry out its day to day activities, continue its business as well as make this change into a cellular system. So, there will be a period where both will happen. The organization continues to produce as well as make changes in the layouts, and over a period of time convert a functionally specialized system into a cellular manufacturing system. So, this period the productivity can go down a little bit, but the organization takes extra effort to make sure that all deadlines are met as well as the change to cellular manufacturing is smooth. Other challenges, implementation challenges, essentially boil down to ability to adapt to change. This is indeed the biggest of the implementation challenges. It is not easy to adapt quickly to change. So, all the people involved in cellular manufacturing are taken through a set of learning programs, orientation programs, programs where they familiarize themselves simply because there is a cultural change. Now, each cell is to be looked upon as a factory within a factory, and each cell has a fair amount of decentralization, autonomy, some amount of powers and so on. So, adapting to that change is a very, very important thing. The last bullet is also about the role of top management. in order for any change in any organization to succeed, it does require a lot of top management commitment, and many times top management provide this commitment and facilitate the smooth changeover process. There could also be issues of operators having to acquire additional skills, operators having to move to different places within the organization to work, operators and people forming groups depending on the specific task, and over a period of time different people would work in different groups. So all these are challenges that the organization faces. Another important challenge which comes as an additional bullet point is aging of cells. In some form this was discussed. The ability of the cell to adapt to volume and variety is another challenge in cellular manufacturing. As time progresses, the volumes increase, the variety also increases, and then it becomes necessary either to increase capacity within the cell or to create new cells. And if the organization is not ready at that point to carry out these, the organization spends a lot of time and effort in inter-cell moves, which is not what a cellular manufacturing system is about. So the ability to adapt or react to increase in volume and variety is yet another challenge, particularly as the cells age. Another challenge as cells age is the machines get older, and as newer machines are brought into the cell replacing some of the older machines, we also get into this issue of operator walking, operator assignment within the cell, number of pieces that each machine can make in a setting. So all these create issues, and all these have to be handled as cellular manufacturing implementation happens. Some of these have been addressed in this course, some of these I have also mentioned about some of these at relevant points, but it is also necessary to understand that there are lots of implementation challenges, and every organization goes through a transition period as well as post implementation. There could be few other challenges, and the need to bring people together to carry out tasks is indeed the biggest challenge. We also touched upon some aspects of applications from industry. Cellular manufacturing has been applied in a variety of industries. Large number of applications come from the automobile industry. There are companies that make machinery, there are companies that make grinding wheels, there are companies that make valves, there are companies that make tractors and farm equipments, and there are companies that make a lot of automobile ancillaries and accessories. So all these companies implement cellular manufacturing. In simple terms, any company that had earlier used a function centric or a functional layout and used batch manufacturing can now use cellular manufacturing, and one can say would have by now started using cellular manufacturing. The field is about 50 years old, and companies have understood the use of cellular manufacturing as a competitive advantage, as a methodology that can create ownership and responsibility, as a methodology that helps improve productivity, almost as a necessary input towards implementing techniques such as just in time manufacturing. And increasingly we find more and more organizations using cellular manufacturing. As I mentioned, any organization or every organization that had a functional specialization now either can move into or would have moved into cellular manufacturing systems. There are also some issues concerning workers coming together to work. These issues are important and these issues are to be handled by the organization. It is also important that people who get along well, who are like minded and can work together, should actually work in the cell. Within the cell there should be perfect unity and harmony among the people who work in the cell. If that is taken care of, then the cell productivity increases. As I also mentioned, there are issues where workers have to undergo training and workers have to adapt, learn to operate newer machines, be more flexible, ready to maintain the machines, ready to transport items from one place or one machine to another in a smaller area where the cell is, which involves a certain flexibility in the entire operating environment of the cells. As also mentioned, there are transition issues to move from one layout to another. We have mentioned elsewhere in the course that in a functional specialization the focus is more on the process, whereas in a cellular specialization the focus is more on the product with large ownership and responsibility. So these issues also have to be looked at when people are implementing cellular manufacturing systems. So in all these aspects have to be looked at in cellular manufacturing, and some of these are practical. Most part of this course I had concentrated on modeling and how we bring quantitative models to look at various aspects of cellular manufacturing. Every now and then I had also indicated through examples how these principles can be used or are being used. Now I believe that these set of slides would reasonably adequately cover some of the practical aspects in the design and implementation of cellular manufacturing. We now move on to just in time manufacturing, also called JIT. Now in the course we had spent a reasonable amount of time on understanding just in time manufacturing as well as understanding Kanban controlled manufacturing system. Some of these points which I might have touched upon earlier, I am repeating, are JIT is involved around the Toyota production system. There is enough literature and references that carry how the Toyota production system evolved and how Toyota as an organization demonstrated the use of these techniques. These techniques came around the early 1960s and again are about 50 years old. So we will see some aspects of Toyota production system, some aspects of single and dual, particularly the dual Kanban system and how the dual Kanban system works. We will also look at Kanban to be understood as a very simple control tool, and then we will spend a little bit of time on push versus pull systems in the context of just in time manufacturing. Now there are several principles on which the just in time manufacturing or the Toyota production system works, and some of these principles I have written here. Some of these we had already seen in the course, but I also thought it will be a good idea to revisit some of these. Now essentially these principles are very simple, and these principles empower the operator or the person who is performing the job. So some of these principles are visual control, displaying the current state of work abnormalities. So wherever there is a small problem or an abnormality, the Toyota production system or the JIT system brings it out through visual controls. So people know, people see that something is not happening correctly. There are some abnormalities and these abnormalities are visible. There is also an emphasis on practical knowledge, which also means that when we go and see, when there is a way to see what is happening, people understand half the issues or half the problems. So the emphasis is on going there, observing, seeing what is happening and understanding. We have also seen that just in time essentially concentrates a lot on leveled production. It is able to handle leveled production and it finds it difficult if there is a lot of variation in the production. For example, if there is a total demand of 6,000 items over 3 days, a leveled production would mean 2,000 plus minus a small amount in each of these 3 days, so that the total is 6,000. A typical example would be something like 1,800, 2,000 and 2,200 making up 6,000 is a reasonably good example of leveled production. But if we have 1,000, 3,000 or 1,000, 2,000 and 3,000 making up 6,000 over 3 days, then we realize that it is not leveled production. Now just in time principles operate very well when production is leveled, and it has to be adapted, and it loses some of its strengths when we are in an environment where production is not leveled. The other principles in Toyota production system are ability to set goals and achieve them one after another. An important aspect which I had not mentioned during the discussion in JIT is the ability to stop the cell if needed. And if there is a machine breakdown or if there is an abnormality, enough power is given to the people who work in the cell. People who work in the cell are empowered to stop production in the cell for a period that is needed if there is any abnormality. So ability to stop the cell is another interesting and important principle, and then immediately the work is done, the abnormalities are attended to, and the cell comes back to functioning. Other principles are principles of continuous improvement and reduction of waste that we saw. I have also indicated the terms that are commonly used, which are Anden, Heijunka, Jidoka, Muda to represent waste, and so on. The next thing that we see is a Kanban system. We did spend some time on understanding the Kanban system, and what I will do now is I will also try to explain how the typical Kanban system works. Now this is a schematic representation. I have also given the reference here of how the Kanban system works. Now let us assume that we have something called a process or a machine that is here. There is a preceding process which is also here. Now let us assume that we have to initiate production in this process. So a P Kanban is drawn from the post and one empty container is taken from the outbound. So let us explain what is a P Kanban and what are these outbound areas and inbound areas, and what is a Kanban post. Now this C represents a C Kanban, or what is called a transportation Kanban in a dual Kanban system. P represents production Kanban, and each Kanban is a card. Now this what I have indicated as process is the current process or the current cell or the current machine on which something is going to be done. Now we also have something called the preceding process. So in some ways we can divide this picture into two vertically. So there are things related to the preceding process, there are things that are related to the process. Now each of this also has a Kanban post, it also has an inbound buffer and an outbound buffer for each one of them. So basically 4 things constitute a process: the manufacturing facility, the cell or the machine or this manufacturing area, inbound buffer which is where some inventory is there, outbound buffer where there is some inventory which is finished goods. Inbound buffer could be treated as raw material for this, and a Kanban post which has these cards for P as well as C. Now suppose we want to initiate production here, then what do we do? P Kanban is drawn from the post and one empty container is taken. So it means when there is a P Kanban that is put here for this person to see, then it means the person can initiate production in this place. So the person picks up a P Kanban and also picks up an empty container from this. So he takes these two. So obviously in order to produce, the raw material also has to be taken. So one full container and a C Kanban is moved from the inbound area. C Kanban is detached and displayed, production begins. So the inbound buffer, a C Kanban is taken from the from its displayed, as well as a full container. F is full and E is empty. So, a full container is taken and a C Kanban is shown. So, this is transported from the inbound buffer to the process. So, the process now has one full container of this raw material and one empty container that has been taken from the outbound buffer. So, as the manufacturing happens in this, all the things that are taken from the full containers, which is the raw material, is manufactured and then it is put into the other container. So, at the end of it, what was the empty container now has a full container of finished items, and what was a full container here now has an empty container. So, production is complete. Now, the P Kanban is attached to the container of the finished item. Now, the P Kanban was earlier taken from here. The P Kanban is attached to the container of the finished item. So, there is a container that has the finished item and is moved to the outbound area. So, the finished container that we have now goes as this F here and goes to the outbound area. The full container that we had here has now become empty and it now goes back to the inbound area. Now, one empty container from the input of the succeeding process and a C Kanban from the Kanban post of the succeeding process is taken to the outbound buffer area of the preceding process. So, now once this is done, this is the outbound buffer area of the preceding process. So, here now I have a lot of empties accumulating and now I have a lot of fulls that are accumulating from the previous process. So, we take one full container from here, one empty container from here, and we swap the Kanban cards as well as the containers. So, the full from the outbound will now come into this inbound and an empty from this will go to this. So, swapping of Kanbans between the containers also takes place. Therefore, full container and the C Kanban moves now to the inbound buffer of the succeeding process and the empty container is placed in the outbound buffer of the preceding process and a P Kanban is displaced. So, what happens is a full container comes here from here along with the C Kanban and an empty container goes from here to this one along with the P Kanban. So, automatically now here you have some P Kanbans and some empty containers happening. So, the process can be triggered in the preceding process. So, this way the whole activity moves from right to left. So, therefore, at the end of this we can now replicate the and say that this is pulling from this and now here there will be empty containers and P Kanbans and this process will happen. Now, by that time something, if there is a process to the right of this, then from that input buffer there will be exchange from this output buffer. So, some empties will come here, some P Kanbans will come here, therefore, this process will also initiate production. So, this is a simple control mechanism through which production is initiated and a pull system is implemented in the Kanban controlled systems. Though in the earlier course I had indicated in some ways the general principle of how it works, I had not taken the trouble of explaining to you how the Kanban system actually works. So, this is how a 2 bin or a 2 Kanban system will work in practice. The last part that we will touch upon in just in time manufacturing is several companies have implemented just in time manufacturing and several companies have also implemented cellular manufacturing and both. Now, a survey was conducted and this is taken from a particular research paper from Mahadevan, who had carried out this research several years ago, and I am explaining some points taken from that research work. So, this is from that research work where a survey was made among several companies that were making different varieties of products, companies of different sizes ranging from small, medium and big companies, and companies which had, some of them had put in some minimum effort of JIT, some of them had put in reasonable effort of JIT and some of them had not put in JIT effort, but perhaps were thinking about implementing just in time. Now several factors were identified, and all these factors can be seen as part of just in time implementation. Now these factors are employee involvement, multi-skilled workforce, setup time reduction, TPM total productive maintenance, TQM total quality management, vendor evaluation, cellular manufacturing, need to produce in small lots, continuous improvement or Kaizen, JIT purchasing, implementation of Kanban systems, quality circles and stable production. Now out of these, companies were asked to rank them in importance that they give towards these aspects for successful JIT implementation, and the order in which these were ranked is actually given here. Now several, almost all companies said employee involvement is the key thing towards successful implementation of JIT. Then of course spoke about multi-skilled workforce, importance of setup time reduction and so on. Now what is important for us is to understand that all the 14 factors are important. It is not that only employee involvement is to be looked at and quality circles need not be looked at. We should not look at this that way. We have to understand that all the factors are important, and organizations have felt that some of them are more important than the other, and all these have been implemented and all these have been used by companies that have successfully implemented just in time manufacturing systems in India. Now I am showing another picture here, and this picture is related to the synchronous manufacturing that we saw. Synchronous manufacturing, theory of constraints. We also saw quite a bit about the principles of synchronous manufacturing, and we also saw a lot of DBR scheduling or drum buffer rope scheduling in this course. Now this picture I have specifically added so that we understand some simple principles here. We also mentioned earlier in the course that 3 measurements or 3 units of measurement were defined in the synchronous manufacturing. They are called throughput, inventory and operating expense. Throughput was defined as the amount of money generated by an organization through sale. Inventory is the amount of money invested by the organization in materials that they intend to sell, and operating expense is the expense or the amount of money spent in converting inventory to throughput. There is also this comparison of a manufacturing system to a troop of marching soldiers. Though I have not shown a troop of marching soldiers, I have shown a set of people who are basically walking one behind the other. One can think of these as representing machines in the organization in some ways. The product moves from one machine to another, and the way the product moves in the organization is like a set of people who are moving one behind the other as batches move in the manufacturing facility. Now there is this comparison with a troop of marching soldiers where we say that the distance that the last person covers is the throughput. Now the difference between, let us say, a trek or a march and a race is almost complete when the first person wins, if there is only one winner. A march or a trek is complete when the last person completes it. So the distance that the last person completes is the throughput. It also in some ways represents the finished goods or finished items that the organization has produced. Now the gap between the first and the last person is the inventory. It is the distance travelled by some and distance not yet travelled by some people. So this gap is the inventory, which means that the last person here has to travel this distance and more. So this is the gap, which is the inventory, which is like the work in progress. Now this is the distance from here, this is the distance travelled by the first person, and This is like the raw material coming in, it goes through, and as the last person completes or as the last process is completed on the raw material is converted to throughput. Now the equivalence of operating expense is the amount of energy that these people spend in walking or covering this distance. So this picture helps us understand the basic principles of synchronous manufacturing, the three measurements which are throughput, inventory and operating expense, and the relationship between raw material, work in progress and finished goods through a representation of either a set of marching soldiers or a set of people who are walking, or linking it to a trek where the trek is complete when the last person completes the trek. Of course, other aspects of synchronous manufacturing that are relevant to this course we have seen in earlier lectures. The last part of this course was on flexible manufacturing, and several models related to flexible manufacturing, particularly in the area of loading in flexible manufacturing, scheduling in flexible manufacturing were considered, and there were models where we said, given a certain capacity in the flexible manufacturing system and given a certain parts, which are the parts that have to be manufactured in the FMS. So we looked at the part selection problem earlier. Now here we look at some of these aspects. Now we had mentioned that FMS is a network of machines, powerful manufacturing machines which are integrated by a material handling system and are controlled by computers. So the material handling system plays a very important and significant role in the performance of a flexible manufacturing system. Now the selection of the material handling system is also important. I had not touched upon so much on this aspect in this course. Even now I am only providing a very brief mention of the role of the material handling system. So material handling systems in FMS involve robots, AGVs, automated guided vehicles, conveyors, monorails and so on. These are also available in different sizes and different capacities for the FMS to choose them depending on the size and scale of the FMS. AGVs or automated guided vehicles are the ones that are most commonly used, and they are essentially battery powered vehicles that move on wires that are kept under the floor, and they relate with these wires and the computer through a set of sensors. Of course, depending on the size of the product that is to be transported and depending on the size of the flexible manufacturing system, other types of material handling systems such as conveyors and monorails and others can also be used. The robots usually are used to carry or take items from the pallets that move on the AGVs and then put it to the machine so that the machines can process the part or piece that is to be manufactured. Another issue in flexible manufacturing is also to define the capacity of the FMS, and we have also seen that FMS is, in terms of cost, it is a very high cost manufacturing system, and therefore the organization has to spend considerable effort in defining the capacity of the FMS that the organization would wish to install. We also would like to spend a little bit of time on the types of industries using FMS. So by definition, FMS is a type of a manufacturing system where we are able to bring the flow shop as well as job shop ideas together. Flow shop traditionally is used for continuous manufacturing, it is used for large volume, low variety manufacturing, while the job shop is used for high variety, low volume manufacturing to middle volume, middle variety manufacturing. Now FMS is one place where we can bring both of them together. I had also mentioned earlier, FMS can be used where the variety is higher and the aggregate volume put together we manufacture a large amount of volume. So those type of industries where there is a lot of variety and the aggregate volume is high can use flexible manufacturing systems. I have personally seen the use of FMS and FMS machines to a very large extent in electronics manufacturing, sheet metal manufacturing and so on. There are a couple of other issues which are financial as well as human issues when it comes to using flexible manufacturing. The financial issues are in terms of the costing and how we are able to cost the product, and because FMS is less of human labor and more of initial setting up cost. So, costing systems in flexible manufacturing are different, and the cost of the product has a larger component of the overhead cost and less component of the labor or cost of using a human resource to make it. So, these are some issues that have to be understood if we look at FMS as a manufacturing facility. Similar thing is about the human issues, because FMS would involve fewer people and more knowledge in terms of using these systems and handling these systems. So, there will be change management issues, there will be implementation issues, and all these issues have to be looked at when organizations choose FMS. It is also, unlike cellular manufacturing, it is not easy to replace the entire existing facility with an FMS. So, many times only a part of the manufacturing is done in flexible manufacturing mode, while the rest of the manufacturing is done in different modes. In such situations also we would have human issues about some people working in the FMS systems and some others working in cellular or more conventional manufacturing systems. So, with this I would conclude this course. I had taken an extra lecture here. I have also introduced a few points that are additional points in the 4 major topics that we have covered. So, in summary, we have covered the 4 major topics in this course. Cellular manufacturing, a very large part of this course was dedicated to cellular manufacturing. Almost 50% of the lectures or more are in cellular manufacturing, and then just in time manufacturing, synchronous manufacturing and flexible manufacturing. While I myself was reviewing this content and while I have received feedback from users and other reviewers, one of the points that was felt is that I could have touched upon or should touch upon some more practical aspects of these methodologies that are being increasingly used in practice. Most of the course concentrated on quantitative modeling, building optimization models, understanding the various aspects in terms of designing the cellular manufacturing or in production control or scheduling or drum buffer rope or machine loading in flexible manufacturing and so on. So, this lecture I have provided some aspects or some inputs on the practical aspects of cellular manufacturing, just in time manufacturing, flexible manufacturing and so on. So, I hope this lecture would add to the knowledge, particularly knowledge concerning the practical aspects of these methodologies. The theoretical, algorithmic and modeling aspects have been covered in the earlier lectures. So, I finish or wind up the course with this, and I wish all the viewers all the best in viewing and acquiring certain amount of knowledge that we have tried to pass on through this course, and I hope that these lectures are useful to the viewers of this course. The references are listed here. Thank you very much, and I wish you all the best.